Great. I'm unmuted and hopefully everybody can hear me as well.
Loud and clear.
Good. So I'm Sam Fuller. I'm a director of marketing within NXP. I've been involved with the ODSA for a couple of years now. What I'm going to talk about for a few minutes is this proof of concept that we've developed, and in particular the PChiplet technology that we've developed. It's kind of a new term that we've coined, a PChiplet, but it refers to a physical chiplet that we're using to explore the technology some more. So within the ODSA track, this is part of a reference design, starting point for new designs, the NXP PChiplet. It's not, when we talk about the stack, the protocol stack, what we're really talking about with the PChiplet and the proof of concept is the exploration of the communications and what sorts of communications and connectivity are going to be required between the various devices that get integrated into a chiplet-based design. One of the things that ODSA is pioneering is heterogeneous chiplet designs. And when I say heterogeneous, I don't mean mixing technology, I mean mixing vendors. So having different chiplets coming from different vendors combined into a single package, and then trying to understand what were the standardized interfaces that those different vendors needed to include to facilitate the development of a multi-die solution built from these chiplets. So that's really the focus of this effort. So when we look at one of the usage models, an important usage model of chiplet technology, the concept of a SmartNIC comes up frequently. And a SmartNIC is intended to be something that provides network connectivity to a server, but is also well placed to offload processing from that server. And there are multiple kinds of processing that can be offloaded. Compute and storage virtualization already have an existing business model, and many companies, many server vendors, especially hyperscale vendors, have already developed SmartNIC solutions that are solving a compute or a storage virtualization offload. There's a set of control and data plane functionality that actually make more sense operating within a SmartNIC than being kind of software functionality in the server itself. And the performance requirements for these devices continue to grow to hundreds of gigabits a second of network traffic and processing. Other areas of offloading include security processing, such as public key, handshake handling, SSL termination, those type of applications, which could be safely moved into a secure SmartNIC and providing the reduction of infrastructure workloads or the infrastructure work on a server. And then, of course, machine learning, training, inferencing, those type of applications. Those aren't specifically tied to a NIC, but could leverage other forms of acceleration. Could certainly be included in the class of cloud offload technologies that are being developed. So within the ODSA workflow, we kicked this off actually last year, and we reached a point earlier this year where we had settled on the design and approach. We focused on essentially a large PCI board form factor that would allow us to develop what we call PChiplets to populate in sort of a mix and match manner within this PCI card form factor. So this design was developed to support QSFP connectivity to a network, PCI connectivity to a host, the ability to plug up to 3 pitchlets or physical pitchlets onto the device, and those could be various combinations. So this allows us to explore different architecture permutations. We also designed the board to support either FPGA or SSDs on M2 slots on the board. So there's a lot of flexibility in the design, and we'll talk about the connectivity of this device shortly. But it was really designed as an exploration vehicle, as the various companies within the ODSA negotiated with one another about what the interfaces would look like and how we could build something like this, and the connectivity of this this PCI card, which essentially would mirror that of a package in a true chiplet design. So one example is this thing we call the Mara board. This is an initial software effort that we're developing to demonstrate the offload of storage protocols, in this case NVMe, over Fabric. So we were able to kind of move that, have a Broadcom NIC that could separate traffic, separate and send storage traffic to this pitchlet, which had both processing and SSD storage on it, to allow that offload to take place. And the Broadcom NIC and LX2, which is the NXP processor, would work together to provide this solution. So we have built these boards. This is a photograph of the ODSA Mara base board. You can see the spot for 3 of these pitchlets. You can see some fans there for power dissipation. This, even though it's designed to plug into a server, in this particular, as we're doing bring up work, we're actually just using a cabled connection to the server. This next slide shows the overall connectivity. You can see between the QSFP ports, the host PCI port, and the 3 slots for the pitchlet, that we're able to route both PCI and Ethernet between the devices. And that was one of the things that we developed and wanted to have that ability to use both of those technologies within the system. And then we're able to develop pitchlets, and depending on the capabilities of the pitchlets and how they're programmed, you can put them in different slots on this board. So this is an image of a populated board showing both, let's see, the base board as well as a Broadcom SmartNIC, a Lattice secure control, management and control pitchlet, and then the NXP multi-core processor pitchlet. So within the NXP multi-core processor, this, I just wanted to explain a bit of what we included here. This is a 16-core ARM architecture device. It's 64-bit ARM architecture, has A72 cores. And it has a broad set of connectivity supporting either Ethernet. It'll actually support up to 100 gig Ethernet connectivity. And it has 6 PCI controllers. It has SATA controllers. And it's got some flexibility in the way the SerDes lanes can be configured to support either the Ethernet or the PCI or the SATA. So all of that connectivity is used in this device. It also has up to 2 DDR4 memory controllers. The pitchlet we built, we populate that with the 8 gigabytes of memory on the pitchlet itself. So this is a photograph of the pitchlet showing, you can see the various sets of connectivity. And one of the important things that we learned was, as we put these things together, you still have requirements for I2C, for FlexSPI, for things like UARTs to support SD boot. So there's a lot of capabilities that, even though you're a chiplet, you still need to bring out these signals, because you have to be able to boot the chip. You have to be able to bring it up, typically through some flash memory interface first. then load in software into the RAMs before you go to the next stage of boot up. You also need some console functionality to understand what's going on. We have I2C connectivity so that we can securely boot the various devices. So we've actually learned quite a bit about the various complexities, especially in a heterogeneous fashion. It's one thing when you're co-designing devices together within a single company. It's quite another thing when you're trying to anticipate or develop something that you believe can be used in a variety of use cases. And so the complexity of that grows. And one of the real values of this proof of concept has been to understand that and anticipate that within the specs that we're developing here. But anyway, this is the current NXP PChiplet. So we're going to take this, the workload. We've got this packaging thing with the PCI Express and the other things that we have right now. And then the intent is to be able to move from the package proof of concept to a die-to-die proof of concept in the next iteration, with moving to new interfaces like bunch of wires, and building test chips for that in the coming year.
Hey, Sam, we're kind of at time right now, maybe even a few minutes over.
Thank you, Archana. Wanted to thank everybody. We've had a lot of people participate in this. It's been a wonderful thing. We're looking for ideas in terms of how we go forward on hardware and software. So thanks for your time.
Thanks, Sam. Really appreciate it.